In this video, we're going to take a look at special beta-oxidation cases. So the classic case of beta-oxidation is saturated fatty acids, which don't have double bonds, but you can also have beta-oxidation cases where you have to oxidize and break down unsaturated fatty acids. And this process is the same as I've written here. So it's the same as saturated, except wherever there's a double bond, you skip the first oxidation step. Because if you recall from the other video, oxidation step 1 is the formation of a double bond, and you don't need to form that if it's already there. So that's the same. So you skip that FADH that gets produced in that first process. So keep that in mind when you're doing ATP calculations. Another case that's special is odd-numbered fatty acids. So odd-numbered fatty acids is the same as even number of fatty acids, so fatty acids with an even number of carbons, except in the last step, one molecule of acetyl-CoA and one molecule of propionyl-CoA is released. So this is because, if you see, if the last video we looked at palmitate, which had 16 carbons. If we add another carbon onto it, that makes 17. So as you can see, we go 2, 4, 6, 8, 10, 12, 14, and then usually this would just break off to become 2 acetyl-CoAs. But here we have an extra carbon, and that extra carbon causes a 3-carbon molecule to be produced called propionyl-CoA, which has its own metabolism, which we'll look at in a second. Now, the propionyl-CoA can lead to the synthesis of toxic intermediates, so when it's metabolized, and this can cause brain damage. So you have to metabolize propionyl-CoA fully, and we're going to have a look at how that happens right now. So let's have a look at propionyl-CoA metabolism. So propionyl-CoA is broken down to D-methylmalonyl-CoA first, and it does this through propionyl-CoA carboxylase. So remember, this is the 3-carbon molecule that got taken off from our odd-numbered fatty acid at the end of the process. So propionyl-CoA carboxylase, an ATP is used, and a bicarbonate ion is required. So in this process, biotin is a cofactor. Biotin is a chemical, and I'm just going to put it up to the side here. Just remember that vitamins are chemical precursors. So that's just interesting to know. So now that we know about this first process, then we have the second process. So we have methylmalonyl-CoA being converted to L-methylmalonyl-CoA, so D to L. They're just isomers of each other. So the important thing to remember is if we don't go past this step, we're going to have some serious problems to the body. So D-methylmalonyl-CoA is toxic to nerve cells, so we have to metabolize it. So to get to the next step, we've just got a methylmalonyl-CoA epimerase, and sometimes you'll see this not written without the D and the L, you just see methylmalonyl-CoA, but there is an extra step here just to convert it into an isomer that can be converted to succinyl-CoA and can be metabolized. So that's why I've written both of the isomers there. So we've got this L-methylmalonyl-CoA, which is formed by this epimerase. And then we have methylmalonyl-CoA mutase, which converts L-methylmalonyl-CoA to succinyl-CoA. And in this process, vitamin B12 is a cofactor. So you have to have vitamin B12 here to assist in this reaction. If you have a deficiency of vitamin B12, this can cause brain damage because it'll lead to a production of methylmalonyl-CoA, which is toxic to nerve cells. This has great clinical importance because if you have a patient who has a vitamin B12 deficiency, you really need to make sure you bring their vitamin B12 levels back up so they can metabolize the methylmalonyl-CoA into succinyl-CoA, which can go to the TCA cycle, and they can remove this intermediate, which is toxic to nerve cells. So that was the special beta-oxidation cases and propionyl-CoA metabolism, which has great clinical relevance, as we saw here. I hope that helps.